Well, good afternoon. This is 12:17 on Wednesday, the 6th of September, 2017. This should be Math 227, Calculus 3. The trouble is I'm the only one in the room, so hopefully the students will be showing up soon. Where we left off last time was, by my mark anyway, was the beginning of 12.5, planes in 3 space. And again, I'm not going to go into this in huge detail, but I will hit some of the high points on it. Here's the figure that's figure 1 in your text on page 664 in 12.5, planes in 3 space. And it's basically illustrating the term normal, okay? Now, that's not normal as opposed to abnormal. That's normal as opposed to at right angles. The term normal is another word for orthogonal or perpendicular to. So basically what you have here is a point P, that's right here, okay, in a plane script P, okay. It seems like they could have used some different letters here. This point P lies in the plane P if the line, or vector, better said, from P0 to P is perpendicular to N. Okay? Now the P0, of course, has to be in the plane. They didn't state that, but that's where they're starting from. And this probably was stated somewhere here. Consider a plane P that passes through a point P0, which is x0, y0, z0. Okay? Well, then this point P is in the plane if that vector is perpendicular to the normal vector to the plane. Okay? And by the way, P0 is the initial point of the vector n also. So that's what we mean by a normal vector to a plane is perpendicular to every vector that's in that plane. Every line segment that's in the plane, n has to be perpendicular to that. Okay? Now, what that means is, of course, that the normal vector is the dot product of the normal vector with that vector P0P has to be 0. If it's perpendicular, the dot product is 0. So we know that to be the case. Now, what they do with that is expand on what we have, okay? The point the point P has coordinates x, y, z. I'm sorry. Let's see. The point P is, let me rephrase that. A linear equation, ax plus by, okay, that's not what we need. Okay, here we go. In this section, we'll show that a line equation, linear equation, ax plus by plus cz is equal to some constant d in 3 variables defines a plane. That's what we're heading toward, okay? So that ax plus by plus cz is some constant, okay? Okay, whatever those values a, b, and c are, okay? That's equal to some constant, okay? And if that constant happens to be ax0 plus bx0, by0 plus cz0, which would be, the x0, y0, z0 are the points of P, and the normal vector ABC, that's where the A, B, and C come from. So the, I think someone's coming in. Yes. No, I'm not Mr. Anthony. What you need? Let me pause. me a couple of notes here. I didn't give the announcements because nobody was in here. This one's sort of minor. I don't think it'll affect you any, but just in case you're looking. Next Tuesday morning, I have a doctor's appointment, and it's at 10 o'clock, but I have to be in there for labs at 9, and that means if I came to campus, I would have to leave by 8:15 to get back to Kirkland Clinic and be parked and into the lab by 9 o'clock. So I'm not coming to campus Tuesday morning until after my doctor's appointment, which I'm hoping I'll be back here somewhere in the neighborhood of 11. Probably not much before 11, but soon after 11 as I can get here. So, but normally I'm in class 8 to 9:30 and 11, so you wouldn't be looking for me anyway, probably. But in case you were on Tuesday, I'm not on campus until probably sometime after 11 o'clock. Okay. That's not my office hours anyway, because I'm in class usually those times. All right, so that's number one, get that out of the way. Number two, I did get all of your stuff into Blackboard. I got the syllabus corrected, and it's in Blackboard. I got the research paper instructions corrected. They're in Blackboard. I have the corrected locator card showing when I'm in class, when I'm off campus, on campus, all that kind of stuff. And then I've got all the PowerPoints for here, and I've got the websites that either students have told me about or I found myself that I thought might be useful, they may or may not. And I've got the link to the YouTube videos. So all that's under content in Blackboard. And I would say I had all the grades posted too, but there aren't any grades. No one's turned in the paper yet. Okay. Now, that's for this course. You're also in 238 right after this, right? Okay. I don't have everything done for that one. I have the syllabus corrected, and it's out there. I've just got to get the research paper pulled over, instructions, the locator card. That's just time is all it takes to do that. And I've also got to get the websites that students have told me about too, and put those in. There aren't any PowerPoints for the next class because they don't provide any. I have them for this class. They're out there, but there aren't any for the 238. And then I've got to get the YouTube video link. You can still get to them, but it'll be easier once you have the link there. Yeah. So that will be for next class. Now, the one other thing, and this is probably one of the most important things. Are you a full-time student here, or you're a transient?
I'm transient.
Okay, from Alabama?
Yes.
I don't know if you, since you are attending classes, you certainly could participate, but I don't know if you have time or desire to. But this is also for folks listening at home. Last year we, for the first time ever, formed a math team, and they do competitions. Last year they did surprisingly well for never having been established before. So they're reforming it for this year, and they'll have competitions. The first competition, the only one I know about so far, will be at Shelton State in Tuscaloosa, either the first or second Friday in October. So it's coming up pretty soon. If you want to participate, you certainly can because you're a student here as well as being a student at Tuscaloosa. Don't know that Tuscaloosa has a math team, but maybe they do. It's mostly for the two-year colleges, but there are some four-year colleges and universities that do participate. So if you would like to participate, it's a fun activity. It really is. Last year, the kids had a lot of fun with it. I helped coach on this campus because some students couldn't get over the Birmingham campus. Miss Nyla Geraci, do you know her? She teaches math on the Birmingham campus.
Oh.
Yeah, she is the coach, but I help over here for students who don't go back and forth that much. So we'll start either today or next week, either both Monday and Wednesday, or at least one day a week, from 3:15 to 4:45, probably in the room next door, 257, just to have practices. We'll get sample problems they've used in other competitions, and just go through easy ways to do them, quick ways to do them, understanding how to go about doing that. And like I said, last year it was a lot of fun. It really was, and you really get to know math a lot better, sort of personally, and in a way that's usable, very usable. So, if you're interested, are you? Do you know if you will be?
Yeah, I don't know if I will be. To be honest with you, because I work all the time. Monday, Wednesdays, it's home and off days. Last year I played on. When do you have practice? What day?
Ours will be on this campus Monday and Wednesday, 3:15 to 4:45. But maybe not the whole time, but sometime in that time block. And Mr. Racy will probably have some practices on the Birmingham campus. I don't know if probably wouldn't be any more convenient for you, but yeah. So you're welcome to come to that, to those. Like I said, I don't know if we're going to start today because I don't have any questions yet, but I'll check with Dr. Thomas to see if she has any of the sample questions.
Like what kind of math will you be doing?
What kind of
math? Like all the problems?
It's, okay. There's sort of two pieces to it. I'm trying to get this right. The one part is a written type thing. I'm trying to remember, get this right in my head. I think the written part, one part basically covers pretty thoroughly everything through pre-calculus, algebra, and trig.
Okay.
And the other part goes into Cal 1 and just a little bit in Cal 2 and Cal 3. I think it's the written part. I think that is the part that's just based on pre-calculus, and the competition, with buzzers and things like this, who gets to answer first, that type of thing. And that's a team type thing. The other's individual. The team type stuff, and you work together as a team. The team comes up with the answer first. I think that's the part that involves calculus, but I may have them backwards. Mr. Racy would know, and Dr. Thomas would know. We did it last year, and I just helped them work questions. I don't remember which ones were for which part. Yeah. But I didn't get to go to this competition because I had things I had to do here. So, but anyway, yeah, you have sufficient math for both parts. I mean, they ask very few Cal 3 type things, if any. So you're a prime candidate for the team, if you're interested in participating. So either let me know or let Mr. Racy know. Do you know Dr. Thomas here?
Dr. Thomas?
Yeah, on this campus. No, okay. Well, let me know, or you can email Mr. Racy, who is N, Nyla's her first name, Jaraysy, N. Geraci at lawsonstate.edu. Okay. Yeah. Or tell me, and I'll be sure to pass that on to her. Njaraysy at lawsonstate.edu. We'd love to have you on the team. All right. Now, seems like there may have been one other thing. I don't remember what it is now. Let me go back and set up what we're doing here. I'd already covered this, but no one was in here. Since you're here and don't have the benefit of going back and listening to what I just said. Okay, here's the deal. Here's a plane P, and this point P0 is in the plane. We know that. That point is in the plane. That point's coordinates are this point P0. Of course, I can't write on it when it's blown up like this, so I'll reduce it again. And let me get my pen colored properly. This is it's a point, and its coordinates are x0, y0, z0. That's point P0. Those are the coordinates. That point right there, those are the coordinates. Here is some other point P, okay? And for right now, we'll assume that point P is in the plane, and we'll say its coordinates are just x, y, and z, because that's a variable point. It can move anywhere in the plane, okay? Here, here, wherever. Here is a normal line from the point P0. And that normal line, it's a vector, okay? And its components are, as opposed to coordinates, components are A, B, and C, okay? Now, and it's normal, meaning perpendicular to or orthogonal to. So it's a 90-degree angle from any ray or line in the plane. The normal vector is always perpendicular to that. Okay? Now, there's the deal. So we're assuming that point P lies in the plane, and we know that point P0 is, so the vector P0 to P, that is in the plane. And if that's a normal vector, then it's always perpendicular to the normal vector. Normal vector is perpendicular to every line in the plane, every vector in the plane. So we know that's true. Okay? Result of that, then, is that the dot product of that normal vector, which has vectors or components. Of course, I go to right and I can't do it, so let me shrink this down. This is vector A, B, C. That's a vector N. You dot that with P0P. Well, P0P would be the vector whose coordinates are x minus x0, y minus y0, z minus z0. Because remember, we said the point P was x, y, z, and the point P0 was x0, y0, z0. So this is the x coordinates of that vector P, that's the y coordinate, and that's the z coordinate. Okay? Now, if that's true, and any two vectors that are perpendicular, the dot product is 0. Okay? So that means the dot product of those two is 0. Okay, let's write what that means. That means A times dot product is this component multiplied by that plus this. Okay, so A times x minus x0 plus B times y minus y0. Okay, and here is our team member. Okay, Jasmine's here. She is on the team. Okay, yeah, the math team. Were you wanting to come by today and start practice? Okay, that actually worked out okay because I just got told over lunch. Okay, let me back up a little. Last Friday, I was on the Birmingham campus as normal. I got there, and usually I am the first one there in the office, so I was there working away, and people were coming by, and neither my boss nor his secretary ever came in. So everything that happened in the office, I had to deal with, okay, including the dean came by to see my boss, the associate dean. And she said, well, just have him tell him I came by to see him. I said, sure. I said, by the way, before you go, the one thing I was going to check with him on while I was there on Friday, because that's the only day I'm over there, said, when are contracts due? Because I was going to ask him that question, but he wasn't there. And I asked her, she said, oh, contracts, I hadn't even thought about that. Yeah, we need to get on that, but it won't be due before next Friday. Next Friday will be fine. It'll be perfectly fine. Yeah, the beginning of the term, I completely forgot about it. Okay? So, Miss Duncan, who's another department chair, about the only other department chair on this campus, just came by my office when I was in lunch. I only have an hour there. And she said, oh, Dr. Pruitt wanted me to be sure to get in touch with you because I've been in class all morning. They sent out an email. They had a cabinet meeting this morning, and they decided they needed contracts today. I could have done them Friday. I could have done them yesterday. But no, they said we need them today. So that means as soon as my differential equation class is over with, I'm going to have to be working on contracts, so I probably wouldn't be able to meet with you anyway. Okay. So sort of good that you have to pick up. Yeah.
That sucks a little bit.
What's that?
That kind of sucks a little bit.
Oh, yeah, but that is sort of normal. Unfortunately, it's not that unusual. Okay. All right, we were talking about, let's set this up again. Okay. What we have here is a plane. That's the plane with the script P. Okay. This point P0 is in the plane. That's given to us. And it's given, it's a definite point, so its coordinates are x0, y0, z0. Okay? This other point P is also, but this is a variable point. It can move around anywhere in the plane, but it's also in the plane. And its coordinates, because it's variable, are x, y, and z. Okay? These are coordinates of a point. The normal vector, the definition of a normal vector is a vector that's perpendicular or orthogonal to every vector in the plane. So it's perpendicular to the plane. That's what normal means, not normal as opposed to abnormal. It means that it's perpendicular to or orthogonal to. And we're told its components of that vector, that's a vector, these are points, are A, B, C. Okay? Now, next thing they're going to do is this, the vector P0P. And if you remember how we named the vector between 2 points, was x minus x0, comma, y minus y0, comma, z minus z0. Those are the components of the vector P0P. Okay? And keep those in mind, because this is true, any vector that's perpendicular to any other vector, the dot product is always 0. Always. So we were just told that this vector n, who has components a, b, c, is perpendicular to, so it's dot product with this vector, x minus x0, comma, y minus y0, comma, z minus z0, that dot product is 0, because orthogonal vectors, the dot product is 0. Now, what I was doing was expanding this and giving the value. This, the dot product is the first component here, multiplied by the first component there, added to the second component here, times the second component there, added to, and that's where we left off, so we'll continue, plus c times z minus z0. I can't write. Okay? And that's equal to 0. Remember, the dot product of two vectors is a scalar. So that's why this has become a scalar. So this says ax minus ax0 plus by minus by0 plus cz minus cz0 is equal to 0. Okay? Now, what you could say from there is that ax plus by plus cz is equal to ax0 plus by0 plus cz0. Okay? If you move these three terms to the other side, add them to the other side, then you get this. And that is what they have here. I'll blow this up. Okay. That's exactly what I've got here. ax0 plus b. This is the fact that the dot product of those two is 0. This is equal to that. Okay. Well, what does that mean? This is the dot product of the normal vector n with the vector OP. That's the vector coming from the origin to the point P. Now, they didn't show that back here, but let me interject in a coordinate system here. It doesn't really matter where you put it. Let's say here's your x, y, z. Okay? Now, this vector here from the origin, wherever that happens to be to there, would be the vector xyz. Okay? The point P has coordinates xyz, but if you do x minus 0, y minus 0, z minus 0, you get that. And the other one was this point. Okay, I'll probably do it at a point that makes it look like they're perpendicular. So there is your vector P0. Okay? And let's go back to this. This is the vector N, which is A, B, C, dotted with the vector OP, which is X, Y, Z. Remember, that was a vector, okay? And that's equal to the vector N, okay, I'm sorry, ABC, dotted with the vector OP, which is, again, from the origin to the point P0, and that would be X0, Y0, Z0, okay? That's what it's saying, okay? Now, all right. Now, this dot product, because this is fixed, A, B, and C are fixed, that's just a constant, okay? And this dot product here, AX plus BY plus CZ, is equal to some constant. You don't have to spell it out, it's equal to some constant. Well, that is now your equation for a line, okay? I mean, equation for a plane, okay? These are two representations of equations for a plane. The first of these is the vector form. So here's our plane. The plane contains one point you know, P0. You've got the coordinates for that point, X0, Y0, Z0. That point is on the plane. You also know its normal vector, A, B, and C. How you know that, they're not telling you, but you know. Okay, you know a point on the plane and the normal vector to the plane. So the vector form of that equation is that n dot xyz, some other point on the plane, is equal to some constant d. And that constant d is this a x0 plus by0 plus c0. The dot product of, in other words, this times that plus this times that plus this times that. That's that constant d. So the normal vector dotted with this xyz that's in any point in the plane, xyz, usually other than this point, the variable xyz, that's the vector form for that. So basically, it's your components of your normal vector times x, the x component of the normal vector times x, the y component of the normal vector times y, z component of the normal vector times z. That gives you the equation equals some constant. And the constant happens to be that same component of the normal vector times x0 plus these things you were given to begin with. Okay? Now, that's the vector form. The scalar form of saying the same thing goes back to your dot product of your vectors, the A dotted with the x minus x, vector P0P, this A times this plus B times that plus C times that is equal to 0. That's a scalar form in x, y, and z. There's a vector form in x, y, and z. Here's a scalar form. Those A and x0, y0, z0, b, c, those are all constants. These are your variables. And it's the same as that. Okay? Now, the other way of writing that scalar form is merely doing that. AX plus BY plus CZ is equal to D. It's also a scalar form of this. Now, what is the D? The D is that AX 0 plus BY 0 plus CZ 0. So anytime you know a point on the plane the normal to the plane, you can write the equation of that plane. And it's really simple. This is it. If you know that normal vector, component of the normal vector x plus the y component of the normal vector y plus the z component of the normal vector times z is equal to some constant. What constant is it? Based on what point is, you know this on the plane, and the ax0 is okay. A lot of blah, blah, blah. Probably need to work a few of them just to see. I wasn't going to work any examples because this is sort of, I'm not sure you'll absolutely need it for the remainder of this course, but it is probably a pretty good thing to know. So here's a plane with a normal vector, and here they give you, there's your normal vector. It's in the z direction, magnitude 3, no components on the x and y. Now, what's that normal to? It's normal to every plane that's parallel to the xy plane, okay? Because that's the only place where, something parallel to the z plane would be perpendicular. So, we know basically what it looks like. It passes through the point 1, 2, 0. Well, that's down on the base, okay? Because z is equal to 0. So it's 1 on x, 2 on y, and 0 on z. So there's your point P0, okay? What does it ask you to do? Find an equation of the plane through that point, okay, with a normal vector. Whoa! They changed our problem there on this. Sorry. Okay, that was for that one, okay? That was a figure here on the side. Okay, forget that. All right, let's do example 1. We're going to use that same, no, everything's different. Okay. All right, no. Let's just do example 1. Find an equation of the plane that goes through the point P0. That point P0 is 3, 1, 0. Not the same problem we have here. 3, 1, 0. There's a point, only point you know that's on the plane. Okay? But you also know the normal vector to that plane. Okay? The normal vector to the plane is 3, 2, negative 5. Okay? It said find an equation of the plane through that point with the normal vector, this normal vector. Okay? Now, it almost seems too easy. Okay? But the equation of that plane is 3x plus 2y minus 5z. There's the left-hand side of the equation. Use the normal, you know the normal vector, use those coordinates, those components as your coefficients of your x, y, and z. Okay? Is equal to some constant. Now we also know what the constant is. The constant is the dot product, basically, of this with that. So that would be 9 plus 2 is 11. What's that? 11. What you? It's the dot product of the normal vector with the vector from the origin to this point here. That would be 3, 1, 0. Okay. So in other words, you dot this and that. That gives you your constant of that. 9 plus 2 plus 0. Okay. That's all there is to it. That's the equation of that. Okay. Yep. Now, this seems sort of dumb, but let's do it. That plane had better contain that point, right? Because we were told that point was in the plane. Well, sure enough, 3 times 3 is 9, plus 2 times 1 is 2, that's 11, plus 0 is 11. Yeah, we're certain that point's on there, and it's normal to this, so, that's it. Okay. That's all there is to that. All right. Now, since we're dealing with normals, or abnormals or abnormal or whatever. It says, keep in mind that components of a normal vector are lurking inside the equation ax plus by plus cz is equal to 0, because that normal vector is ABC. So they're right there. The same is true for lines inside R2. This is a line in R2. Okay? That's just regular two-space, XY plane. Okay? Now, in the XY plane, that normal vector also has to be in the XY plane. So you want a line normal to this other line. And the line AX plus BY is equal to C, which is this green line right here, including the blue portion of it. Okay? That's AX plus BY is equal to C. Okay? And if you wanted to, you could say where Y is equal to 0, your X would be C over A. That happens to be a negative number in this case, because that's where that line would cross somewhere out here. And where X is equal to 0, that would be here, anywhere along the Y-axis. So you know right now where X equals 0, Y is equal to C over B. So this point right here has to be C over B. Not that we need to know that, but that's just giving you what you know, pretty obvious right off the top. Okay. Now, yeah.
Excuse me. I just want to make sure of something. So, a normal vector in a 2D plane, like, it can also be normal if the arrows point downward.
Yes.
So it can still be normal. Like that.
Yeah, that would be another normal.
So in a 3D plane, it just pretty much got to be perpendicular. That's all
right. Yeah. And okay, that's a very good question. A very good point. Okay. And in that case, well, let's not use that one because that's so simple. This one. Okay. If you extended this red line down like this, that's also normal to it. And then what would happen? Okay. The components then of that, the negation of that, would be negative A, negative B, negative C.
Yeah.
Okay? That's just everything's going in the opposite direction. Okay? And then you could say the same thing, that the dot product of that and that previous one that we did, okay, let's go back and do that. Oh, where is it? I thought we did it. Where is it? Oh, here it is. Okay. So, what you're saying, here's another normal, -3, -2, 5. Okay? That's also normal. That's not this one, but it's also normal to it. Okay? Well, its equation would also be -3x minus 2y plus 5z is equal to, and then what would we do there? We would dot these two together, -9 minus 2 more is -11 plus 0 equal -11. That's the same equation. Okay? It's the same equation. You just multiply this by -1. Both sides by -1, you get 3x plus 2y minus 5z is equal to 11. Yeah, because you do the opposite of that. When you dot it with that point, it's going to give you exactly the opposite there. So yeah, both of those are normals. Okay, a little bit later, when we start talking about curves, the curve will have two normal lines too, but we count the normal line, well, we'll get there. Okay. With the curve. With planes, you can do either one. Okay. So we'll just leave that alone. Okay. Now, where were we? Here. Okay. Okay. The line AX plus BY is equal to C in this figure here has a normal line, and its normal line is the vector whose component are AB. Okay? Now that may not be completely obvious here, but let's just see what we can deduce from that. Because it has a slope of, okay, the slope of this line, okay, I'm going to have to reduce it. Let's write this in slope-intercept form. That would be BY is equal to minus AX plus C. Agreed? So Y is equal to minus A over B X plus C over B. Okay? Where C over B, remember we said was the y-intercept right there. We already determined that. Okay? Let me clean that up so it's easier to read. Okay? So the slope of this line is minus A over B. So the slope of this line, and we don't really care about the y-intercept, but there it is. We already determined that. Okay? Now, if that is your normal vector, AB, okay, what is its slope? Not 0, definitely not. 0 slope would be horizontal line. That's not horizontal. Okay, no. The slope of that line would be how to convince you of it. Let's draw this vector down here, this red vector. Let me change the red so you'll know what I'm talking about. Okay? Let's see if I can draw that looking like it's just about parallel. Is that close enough? Yeah. Okay, that's N, right? Let me go back to black then, or dark. Okay? Dark. Okay. So this N is also the vector AB, right? Now that means it's A units on the x-axis, which looks like here, let's call that a minus 1. And B units up here, let's call that a plus 2. Okay? You don't have to, but that would be that vector, right? Yeah. Right. Okay? So what is its slope? Rise over run. Plus 2 over negative 1. Right? Which was plus B over A. So if its slope is B over A, the M for the normal vector is B over A, and the M for the line here is minus A times B. Guess what? The product of the, well, a vector perpendicular to this one will have the negative reciprocal. The negative reciprocal of that. Yes. Those are perpendicular. So all we have to do is find the slope of this one, and you know its perpendicular line would be the slope of B over A. And that's exactly what the slope of that normal vector is. B over A. Right? Okay. All right. So therefore, it has to be perpendicular to it. Now, you could say, if you did minus A minus B, that would also have the slope of B over A. Okay, but that would also be normal to both of those. Okay. I think we beat that in the ground, haven't we? Okay. Let's go to the next thing here. This is example 2. Okay? And this sort of follows from what we just said. Let P have an equation. This is that plane with an equation. 7x minus 4y plus 2z is equal to minus 10. That's this one right down here. If I blow it up, then I can't write on it, so I think I'll just leave it here. That's that equation here, that bottom plane that's sort of hidden mostly by the other two. Okay? Find an equation of a plane parallel to that passing through the origin. Okay? Well, the plane parallel to that passing through the origin, guess what? If it's parallel to it, it has to have the same normal vector. And that normal vector would be 7 minus 4, 2. Because every plane parallel to it has to have that same normal vector. So if it passes to the origin, then x, y, and z are 0. There's a point on it. So that would be this plane right here. And if it's passing through the point 2, -1, 3, so here's some point Q, 2, -1, 3. All right. Then the dot product of the normal vector and this must be your constant on the right-hand side. So that'd be 7 times 2 would be 14. Minus 4 times minus 1 is plus 4. And plus 2 times 3 is 6. That'd be 24. There's that. So all these three planes are parallel because they have the same normal vector. This, okay? So they're all three. This one down here was minus 10. We don't know what point passes through it. There's several points that pass through it. The origin, though, we know it's on that middle one, so that has to be equal to 0. Because 7 times 0 plus minus 4 times 0 plus 0. Okay, because the origin is on that one. And this one, that point's on it. So now the dot product of these, in other words, you just plug this in. This part, 7 times this minus this times this. That point has to be on the plane. That's equal to 24.
How did you get to -1 and 3?
How do I get what?
To -1 and 3 Q.
How do I get?
I need that point for Q.
Oh, they gave it to us.
Oh, they gave it to you?
Yeah, they said
okay.
find the equation of a plane that passes through, that's parallel to this plane that passes through that point.
Oh, okay.
Obviously, this plane doesn't pass through that point. You can plug it in, no, it won't. But if you plug these values in for this part, find out what it is equal to, that plane is parallel to this one because it has the same normal line. So that means they have to be parallel to each other. It just has a different constant. So that means it's basically a vertical shift up of the plane, the whole plane. Here's the plane, it just moves up. It could move this way as long as it doesn't change direction. Yeah. It's parallel. Okay. All right. Now, this is for that problem we just did, this is the general equation for all the planes that are parallel to that first plane. You just put a different D in there. How do you get the D? If you know a point on the plane, plug in those values and you get your D. Okay. All those will be parallel to one another. Okay? Now, this is, I don't know how long I'll need this, but let me at least set it up so we can use it. Here are 3 points, P, Q, and R. Any 3 points define a plane. Well, that's not quite true. If here's a point, and there's a point, and another point on the same line, they don't define a plane. But any 3 non-collinear points define a plane, whichever plane that is. Because any 2 points define a line, do a third point that's not on that line, you've now defined a plane. A plane like this, a plane like this, a plane like this, it defines a plane. Any 3 points, non-collinear points define a plane. So 3 points, P, Q, and R determine a plane, assuming they don't lie on the same straight line. In other words, they're not collinear. Okay. So how would you get you're given the 3 points, okay? How would you determine what that plane is? What would be your equation of the plane? Well, let's go back to what we know. Okay. You're given 3 points. Pick any one of those. They chose P to be the point you're going to put the normal from. And then do PQ as a vector and PR as a vector. 2 different vectors, okay? Not on the same line, okay? 2 vectors. Now, if you want something perpendicular to that, do a cross product, okay? So they do vector PQ cross with PR, or PR cross with PQ. It doesn't matter which one you do. One's going to produce a vector that way, the other's going to be the normal vector that way, both are normal vectors. Okay? You know both of those, so you can express that as components. This would be, let's call it x sub r minus x sub p, comma, y sub r minus y sub p, comma, z sub r minus z sub p. That would be this vector. That would be q, x sub q minus x sub p, yeah, blah, 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 blah. And then you do the cross product of those 2, and you know all those numbers. They gave you that to begin with. So you can figure out every one of those. Cross the 2, that gives you your normal vector. Once you have the normal vector, you have the coefficients. And then plug in any one of those points, preferably B, that would be the easiest one, in that you get what it's equal to. So pretty easy to come up with the equation. Okay? Do you want to do one? Example 3 is one of those. Huh? Yeah. You do want to, okay. So let's, P, they said was 1, 0, minus 1. I don't think that fits here. Yeah, no it doesn't. But let's just say it did. Okay, P is 1, 0, minus 1. I'm certain that's not point P as drawn here. Q over here is the point 221. That's probably not reasonable either for this drawing. And R is the point 412. Okay? Now, it says find an equation of the plane P determined by those 3 points. Okay? Well, we know that the point PR, the vector PR is on that plane, and the vector PQ is on that plane. Okay? Well, PR is this vector. Those are points. Here's the vector. PR would be, you tell me.
It would be only 4 minus 1.
Yeah.
4, yeah. 1 minus 0, 2 minus 8.
Which is?
1. I mean, I'm at 3.
3. Okay. Okay. And do PQ.
You just give the numbers.
Yeah. 1, 2, 2. Okay. Now, those are 2 vectors. Okay. We're going to cross them. Okay. Remember how you cross vectors? Sort of the easy way is I, J, K, 3, 1, 3, 1, 2, 2. Okay? Now, the easy way to cross that is this. Repeat the first 2 columns. We haven't done this, but I think it was in the book. 3, 1, and J, 1, 2. Okay? And now you sort of do like you're going to do a determinant. Okay? And you do this. That would be 2I, you're multiplying down, plus 3J, plus 6K. Now you do the uplands. Minus K, and the ones going up are always negative, minus 6i, okay, I can't write, okay, and minus 6j. Okay? So that would be minus 4i minus 3j plus 5k. Okay? That's the cross product between those two vectors.
In other words, that's the normal vector.
That's what?
That's normal vector.
Okay? And that's going to be the normal vector, a normal vector to that plane. Exactly. So the equation for the plane would be minus 4x minus 3y plus 5z. Okay? But now we need to get your constant, that d, whatever that is. Well, let's take the point P, this point right here, and cross it and dot it with this. That's your normal. This is the normal. Okay? So that would be minus 4 plus 0 minus 5. That's equal to minus 9. Okay? Now, if you don't like all that many minus signs, change it to 4x plus 3y minus 5z is equal to 9. I like that better. Same thing, you just multiply by minus 1. Okay? Let's see what we got. 4x plus 3y minus 5z is equal to d for some d. And what d do we choose? 9. Okay, that's it.
In this question, it said what point to put in.
What's that? Yeah, they told you the 3 points.
Okay.
Given 3 points, you can come up with the equation of a plane. Okay. Now, let's see what this one's doing. This, by the way, looks like example 5 here. Traces of a plane. Do you know what the term trace means? The intersection of a plane P with a coordinate plane or a plane parallel to a coordinate plane is called a trace. Okay? So here's this plane P. You see it hanging down there. And here's your x-axis, there's your y-axis, and there's your z-axis. Okay? So let's take the xy plane here. Okay, so z is equal to 0. That's basically this plane here. This is the trace of that plane, the xy plane, and the plane P that you were given. In other words, where does it intersect? Okay?
Say that again.
Okay. All right. Here's the plane, right here. 2x minus 3y plus z. Take their word for it. That beige-looking thing there is that plane.
Yeah.
Okay. Okay. Now, here's a hint of how you draw that plane. They drew it for you, but here's a hint. Okay? This is the equation of the plane you have to draw. Let's initially pick some points. Okay? Be clever about it. Let's put x and y is equal to 0. That means z is equal to 6. When x is 0, y is 0, z is equal to 6, that point's on the plane. Right? And let's do the same here. Let's let y and z be 0. Minus 2x is equal to 6. That means x equals negative 3. X equals negative 3, that's on the plane, right? Okay? And then let x and z be 0. 3y is equal to 6. Y is equal to 2. That's on the plane. Okay? So those are 3 points where that plane crosses the x-axis, the y-axis, and the z-axis. Okay? Now, where it crosses the x-axis and the y-axis, That's where z is equal to 0, because this is where x and y is equal to, I'm sorry, x and z is equal to 0, that's where y and z is equal to 0, that's where x and y is equal to 0. So these 2 points, z is equal to 0 on both of those, right? So this line right here is the trace of that plane on the xy plane. And you know 2 points, you know y is equal to 2 and x equal to minus 3. Okay, so let's identify, okay, I got to shrink back. Okay, so this is the point right here of 0, 2. This is on the xy plane, right? And this point right here is minus 3, 0, right? On the xy plane. From that, you can tell the slope of that line would be y, okay, m of that line would be, pick either one of these, they make that y2 minus y1. So let's call this point P, let's call this point P2, this point P1, okay? So that would be y2 minus y1 would be 2, and x 2 minus x1 would be 3. So the slope of that line is 2/3, okay? And the y-intercept, that would be here. So y is equal to 2/3 x, and the y-intercept is plus 2. So multiply both sides of the equation by 3, and you get 3y is equal to 2x plus 6, right? So 2x minus 3y is equal to minus 6, or minus 2x plus 3y is equal to 6. Whichever way you want to do it, there's the equation of that line. Okay? Then you can do the same thing with these 2 points, only now you do the YZ plane, so you just don't even have x in there at all, and use those 2 points, come up with a slope. You have to figure out which one. You want z being like your y and y like your x, however you do that, but you come up and you get an equation for that line. Now, let me show you an easier way. Okay? In other words, that first one was where z is equal to 0. Looky there. Minus 2x plus 3y is equal to 6. Where x is equal to 0, 3y, x equals 0. So that would be here, that x equals 0 is there. So now you're in the YZ plane. So that would be 3y plus z is equal to 6. And there it is, 3y plus z is equal to 6. And then we're, y is equal to 0. Now you're in the xz plane. And that's this one. There's minus 2x plus z is equal to 6. Okay. Really easy to do. You get your intercepts, you get these traces. Those three blue lines are your traces, and you get them just by making one of those. Say, if you want the xy trace, then you make z is equal to 0. You want the xz trace, you make y is equal to 0, and that yz trace you make 0. So you've got those 3 traces. You couldn't get much easier than that, right? Okay. And how you got the points? You make that x and y equals 0, that gives you the point of it, yeah. So, pretty easy to do. Okay? So, all right. That's it for 12.5. I hope we didn't take too much time on it. Let's move to 12.6. This is where, frankly, the course is supposed to begin. But that was all background. Sorry it took us that long to do it. Why is it not advancing? There we get it. Okay. So let's get out of this. And we're in 12.6 now. And this is where your first test will begin. 12.6. All right. Now, let me blow this up. Ugly as it is, okay. This is your generic equation. Okay, let's start over. A quadric surfaces are the surface analogs to conic sections. Now, we didn't really do conic sections, but are y'all familiar with those? Your conic sections could be circles, ellipses, hyperbolas, I think that's most of them, parabolas. Okay. Now, any idea why they're called conic sections? Okay. If you were to draw two cones, okay, a cone has a point here, and it's coming down like this, and from the same point it's going up like this, okay? We usually think of a single cone, but, a cone is typically two of them, point to point, That's a cone, okay? Some revolution around. Okay. If that is a circular cone, in other words, if all say it goes through the XY plane at the origin, and they're all circles going up and circles going down, any plane parallel to the XY plane is going to be a circle. It intersects with a circle, here or here, okay? So that makes your circles, okay? Now, if you tilt that plane slightly, now you make an ellipse, okay? Got it? Tilt it just a little bit and cross that, and now you got it in the ellipse, okay? Do a plane perpendicular to it, and you get hyperbole, okay? What's that? Okay. I'm trying to think if conic sections are anywhere in the book. Maybe the first chapter. Let's see if it's in the first chapter. So my arm waving leaves a lot to be desired. Conic sections, 609 to 619. Here we go. If you have your book, turn to page 609. Huh?
I got the James Stewart.
Okay, look in your index and see if they have conic sections. C-O-N-I-C. Well, if you don't want to do that, here, I'll do it here. Hang on to where I'm supposed to be. Okay. There's your cones. Okay. Now, I already described to you if that's a circular cone, any plane other than the XY plane, parallel to that is going to make a circle. Okay. If you tilt it like this, you get an ellipse. If you tilt it down here and only cut part of it, you get a parabola. And if you tilt it that way, you get a hyperbola. You get one here and one there.
Okay, you talking about tilting the plane?
Yeah.
Okay.
Taking the plane and cutting that cone in 4 different ways. Parallel to the XY plane, you get a circle. Tilted to the XY plane, but cutting completely through the cone, you get an ellipse. Tilted to the plane, any of the planes, but only cutting one part of the cone, you get a parabola. And then parallel to either the X, Y, or any of the planes parallel to the Z-axis, that's going to form a hyperbola. And that's why you call them the conic sections. Okay? You make them all using cones. So, the quadric surfaces are the surface analogs, where those were planar figures. Now we're going to do three-dimensional figures. So rather than talk about circles, we'll talk about spheres. Rather than talking about an ellipse, you talk about an ellipsoid, basically almost like a football. Right? If you rounded the ends of a football, that would be an ellipsoid. A paraboloid would be a parabola spun around, and that would be, I can't think of anything that would be shaped like that. And a hyperboloid would then be something that's, you take a parabola and spin it around an axis, and you get, basically almost looks like two paraboloids, but they're not, but going in opposite directions. Those are your conic sections. Your quadric surfaces. They're now surfaces, not planar figures. This is the generic equation for any quadric surface. Okay? You have your x, y's, and z's in three dimensions, x, y, z. You have the pure square terms. You have the various cross terms, x, y, y, z, and x, z. And then you have sort of the linear terms, and then you have a constant, and it's equal to 0. Okay? And these would make any kind of a quadric surface you could dream of. Okay? Now, the coefficients here, capital A, capital B, capital C, capital D, capital E, and capital F, those are all basically quadratic terms, second order terms. A, B, and C are linear terms, that's a constant term, so all those together. Those could be positive, negative, fractions, decimals, rational, irrational, or 0. Okay? We aren't going to include anything with complex numbers. Okay? We'll keep that. But, depending on who's positive and who's negative, that will determine whether you have an ellipsoid, a hyperboloid, a paraboloid, or what. You know, whether they have a linear term or not. Now, right off the bat, we're going to say the D, E, and F, we're going to say all those are going to be 0. We're not going to deal with any that have these cross terms. So we're only going to have pure squares, linear, and constants. We're going to eliminate these. We're not going to do those. Those would be, you know, somewhere other than where you want to be. Okay, so those make it really complicated. All right, the quadric is said to be in standard position. Okay, wait, I'm sorry. When the coordinate axes are chosen to coincide with the axes of the quadric, the equation of the quadric has a simple form, and it's said to be in standard position. And in standard position, that's when you don't have these. It's only when you had your cones over here somewhere, there's your X, Y, and Z, and you had your cone like this, you know, doing like this. Then you get all sorts of cross terms and stuff. We're going to have the quadric surfaces. These are going to be 0. So the quadric surfaces are all going to have an axis either along the x-axis, the y-axis, or the z-axis. No x, y, y, z, x, y, z, or any of the others. Okay, so that's going to be standard position. So don't worry about the cross terms. The x, y's, y, z's, and z-axis. Not going to have any of those. Okay, don't try memorizing formulas either. Okay? Now, here is an ellipsoid. Okay? Now, here is your equation for ellipsoid. Now, I don't know, let me back up here and do something else first. I did it last time I taught this course, and I found it worked better. Let's start with our conic sections. I want you to give me the simplest form of an equation of a circle. Do you know what that is? X squared plus y squared r squared. We're only in 2 dimensions here. Circle would be 2-dimensional. Okay, not 3-dimensional. No z's in it. That would be the simplest equation. Okay? X squared plus y squared is equal to r squared. What's r? The radius of your circle. And that circle is centered at the origin. You don't have x minus a squared, y minus b squared. You don't have any of that. Those would be circles not at the origin. We're going to get at the origin, standard position. Okay? So that's it. Now, I want to change that ever so slightly. R is positive, right? A radius. You know, you can't have a negative radius. You can't have a 0 radius. That's not much of a circle, is it? So it's some positive number. And because r is positive, r squared is positive. Okay? And not 0. Right? So let's divide all 3 of these by r squared. So your actual expression for a circle would be x squared over r squared plus y squared over r squared is equal to 1. That is your another expression of the circle. That's a little more consistent with what we're going to do in quadrant surfaces. Okay. Now, do you have an idea what an ellipse is?
Yes.
Okay. In an ellipse, you don't have a radius. You have a major axis and a minor axis. Okay? So basically, an ellipse, this is a circle. Okay? An ellipse then would be like this. Second, x squared over a squared plus y squared over b squared, that's equal to 1. See, for an ellipse to be a circle, a and b have to equal each other. The minor axis and the major axis are the same, so you have a circle. If they're not the same, then you have an ellipse. Okay? So that's your equation for an ellipse. Okay? You can't really go back and do one like this because a's and b's aren't the same. But that's your equation for an ellipse. Okay? Now, your hyperbola. And you can do it either way here, but I'm going to do it this way. X squared over a squared minus y squared over b squared is equal to 1. That's a hyperbola. Okay? Now, obviously here, the origin is not on that circle, right? Because x can't be 0 and y can't be 0, but that would be 0 plus 0 is equal to 1. That's not going to happen. Okay? Neither could 0, 0 be on that because that would equal 1. Neither could 0, 0 be on this one, but for a different reason. Here 0, 0 is inside the circle. There it's inside the ellipse. Here it doesn't even come close. Okay? And here's what to do. Okay. First picture this where y is equal to b. No, okay. Let's do y is equal to 0. Okay, then obviously x equal a. Only choice for that equal 1, right? So that gives you x equal plus a or minus a. Okay? And then for any other y, it does like this. So that's what makes you there. Now, can x ever be 0? No, well, that's always negative, and that's always 1. Okay, so x can't be 0, so therefore you don't have any place. In fact, x can't be anywhere between minus a and plus a, because if x is between minus a and plus a, this number is less than 1. And you subtract that from 1, you get a positive number, and this is obviously a negative number. So x can't be anywhere from plus a to minus a. So then it goes like this. That's your hyperbola. Okay? Kind of makes sense? Now, parabola. Y is equal to x squared, or y is equal to ax squared, or something like that. That's your parabola. Okay, you know that is, yeah. Now you can add other terms in it and stuff, but that gets off standard position. Okay, so that would be it. Okay. Now, how else could we express that? That could be x squared minus y is equal to 0. But this, we'll come back to that. Okay, but that's your parabola, basically, stuff like that. Okay, or ax squared. Okay. All right. Now, let's go back to this. What's your ellipse? Here's your ellipsoid. Now, what makes that an ellipsoid? Well, that kind of looked like your ellipse. Remember, your ellipse was this, x squared over a, or I didn't write it this way. I said x squared over a squared. You could have said x over a squared, which y would be squared is equal to 1. Put a third dimension in it, you got an ellipsoid. That's it. Okay? Now, notice when z is equal to 0, you're just in the xy plane, and then you have an ellipse. And there you have the ellipse in the xy plane. Right? Whoops, wait. This one right here. It's hard to see. It's light blue back here and dark blue right here. Okay? When y is equal to 0, then you're in the xz plane, and there you have an ellipse there. Okay? It almost looks like a circle here, but it's not guaranteed to be, because when this is 0, your a is one axis and c is the other axis. And when x is equal to 0, that would be the yz plane there. Here's your ellipse. C to minus c. There it is. Okay. You all know the axis. So every way you cut it, you get an ellipse. Okay? And not just every way you cut it on the xy plane. Every plane that you do parallel to that forms an ellipse. And parallel to this one forms an ellipse, as long as you don't get beyond A or B or C. And parallel this way, you get an ellipse. Okay? So the ellipsoid, all those are called traces, by the way, just like we used it before. Those traces are all ellipses. Every one of them. Okay? And that's your generic form, the standard form for an ellipsoid. Okay. There's the equation. Same one they had here, only they put it in a box here. Okay. So anything you get that's like this, every variable is squared, and you have plus signs with all the variables and a plus one on the other side. That's your ellipsoid. All right. All right. Surfaces are often represented graphically by a mesh of curves called traces, obtained by intersecting the surface of a planes parallel to one of the coordinate planes. Okay, that's what I was talking about before. In fact, this next picture may show it a little bit better. Okay. Here's that ellipse we saw before, and this is on the xy axis, this one down here. We've gone z is equal to z0, something a little above that. Well, that forms an ellipse. If you went a little higher, you'd form another one. So you got z is equal to, what was that, c, then you have a point. Anything below, between minus c and plus c, you're going to have a little bit of an ellipse, as long as you don't get up to either one of those. This will be a little bit smaller ellipse, and a little bit smaller, and a little bit smaller. Right near the top, you just getting closer and closer. Those, anytime you intersect a quadratic surface with a plane parallel to one of the coordinate planes, the XY plane, the YZ plane, the XZ plane, any of those are called your trace curves. So this is the one where Z is equal to Z0. That plane is parallel to the XY plane. That's where Z is equal to 0. And you have another ellipse. Okay? Every intersection, every trace of an ellipsoid is an ellipse, no matter which plane you use. Okay? Make sense? All right. So, all right. Example 1 was here, and here it is. X over 5 squared plus y over 7 squared plus z over 9 squared, okay, is equal to 1. First, what is that? It's an ellipsoid. Now, you have all pluses, that's an ellipsoid. It's equal to plus 1. Okay. Now, what's the question? Describe the traces of that ellipsoid. Well, first, I would say identify some key points on the ellipsoid. Let's just say that this one. Right here would be the point 5, 0, 0. Back here, that point would be negative 5, 0, 0. Okay? Yuck. I put my parentheses right over my minus sign. Okay. Okay. The y here, this would be, I don't think they've drawn it to scale here. This would be 0, 9, 0. And this one would be, this is not the right one. This would be 0, minus 9, 0. The z, this should be, I'm sorry, those are 7s. I'm sorry. I was looking ahead, saying that it can't be true because the z, obviously z scaled differently, because this would be 0, 0, 9, and the one down here, wherever that is, would be 0, 0, minus 9. Okay. Those would be the key points you might say on it. And then I would go on and draw the planar, the coordinate plane ellipsoids and ellipses in there, just to have a basis. And they do have them here. It's just hard to see. There's your XY plane. There's your XZ plane. And it's so hard to see the YZ plane, but it's there too. Okay. And it said, what did it say? Describe the traces of the ellipsoid. Okay. Well, every one of them an ellipse. As you go to z equals z0, z1, z2, up to 9, then you get little smaller and smaller ellipses. Okay. If you do the ones along the y0s, that would be in the parallel to the xz plane, you would have smaller ellipses coming out here and going back there. Okay. And the xz plane, small ellipses coming here and there. XY planes with the z0 can go anywhere between minus 9 and 9, not counting minus 9 and 9, but anywhere in between. The XZ planes will go anywhere from y is equal to minus 7 to plus 7, not counting that. There you drop to a single point, anywhere inside those. And then the YZ plane parallel to that would be anywhere from plus 5 to minus 5, x equals that. Just not those final points, but anywhere between. Every one will be an ellipse. Tiny little ellipses are on this field. That's really all you can do. And I guess to say it a different way, in the xy plane, it would be x over 5 squared plus y over 7 squared is equal to 0, because there z is equal to 0, okay? And in the yz plane, the trace in that would be y over 7 squared plus z over 9 squared is equal to 1. Oops, I said 0. It's not 0. You should have caught me. Okay, 1. Okay. And in the xz plane, it would be x over 5 squared plus z over 9 squared is equal to 1. Okay? Those would be your coordinate plane ellipses. Okay? And then anytime, say z was something other than 0, but some number, let's say 1 or 2 or 3, or anything other than anything between plus and minus 9, okay? Anything in between there, that's going to be a fraction smaller than 1, and you subtract it here, you have a smaller and smaller ellipse, okay? So yeah. But you see, z can't ever be greater than 9, because then that last term is greater than 1. You subtract that from the other side, you have negative, and this is positive, so you can't have it. That's the limit. Okay. All right. I think I wish they had shown this. They don't show. This is a better picture because that's obviously not this one. Here's the one that we have here. The x's are going from -5 to 5, the y's are -7 to 7, the z's from -9 to 9. And they show the coordinate planar ellipses here. There's the yz one, the red one's the xz one, and the blue one's the xy one. Okay? And then the ones parallel to this are the ellipses going up and down. The ones coming out here are the green ones, coming out the x-plane from -5 to 5, and the red ones are the ones going up and down the y-planes, like this. So the blue ones are up and down the z-planes. I can't hold this thing for me. So that's what it's asking for. You can see those ellipses. All right. Now let's move to our hyperboloids. Okay, you have two kinds. 1 sheets and 2 sheets. Okay. Now, I do not like the way they express them, and there must be a reason they express them this way, but to me, it's not as consistent with what we call the conic section. Here's how I would express this one. I've got to shrink it if I'm going to write on it. X over A squared plus Y over B squared minus Z over C squared is equal to 1. That's your hyperboloid of 1 sheet. Okay, now what does that mean? To me, it makes more sense this way, because what I can do is say, let's let Z is equal to 0. What do we have there? Huh? That's a plus sign. And that's an ellipse, exactly. Okay? So you have ellipses up and down the Z-axis. Okay? And it's 1 sheet because it doesn't ever go to 0 there. So that's an ellipse. Ellipses, all these traces that are parallel to the xy plane are ellipses. Okay? Now, you said y is equal to 0, what do we have? That's a hyperbole. Okay? So the xz planes, that's this one, you have them going like this. Okay? And in the YZ plane, where x is 0, hyperboles again going that way. Okay? So to me, that makes it a lot clearer. This is not as clear to me. Okay. Now, the two sheets one.
What did it mean by two sheets?
Okay. Let's show the picture, and then we'll come back to it. Why they have these out of order, I don't know. There's what I was holding my book up to show you. That's your ellipsoid. I can't explain to you why they don't. This is what we're doing it for. This is minus 5 to plus 5 on the x-axis, minus 7 to plus 7 on the y, minus 9 to plus 9 on the z. The blue circle is in the YZ plane, the red circle in the XZ plane, and the green circle in the YZ plane. Okay? And then, parallel to the blue circle, those are your traces for constant z's, positive or negative z's, going up or down. Those are your blue circles there. Your green circles are various values of x, and it's dependent only on y and z. And then your pink circles are various values of y, and it depends only on x and z. Okay. And every one of these is an ellipse here, and these are ellipses going this way, and these are ellipses like that. That was this thing I was holding my book up for because I didn't think they had it on the slideshow. Okay, now let's get to your, here's your hyperboloid of one sheet. Notice, in the xy planes, your traces are all ellipses. All right, see those blue things? The thinnest on the xy plane, they get bigger out and bigger down. That's one sheet. Okay, the one of two sheets, I'll light this up a little bit for you. Okay, of two sheets, they notice that your traces in the parallel to the xy plane, you don't have a trace on the xy plane. We'll go back and look at that. But at some point, you start getting traces, and those parallels are ellipses again, just like they were here, getting bigger. Okay, and your traces along the x-axis are hyperboles, and along the y-axis are hyperboles. Along the z-axis, where you have them, are ellipses. Now here's the deal with that. Let's go back to our formula here. Okay. If you look at this, this time, in this way, at least to begin with, this form is actually a little bit better. And here's why. You see that z always has to be greater than c. If it's equal to c, then you have a 0 here. Okay? And then it has to be x equals 0, y equals 0. Okay. C can't be less than c, because then this ratio is less than 1, and when you subtract 1 from it, you get a negative number. C can't be negative, ever. So this says that your z has to be greater than positive c or less than negative c, because this value has to be 1 or greater for this to make sense. If it is exactly 1, then you have 0, 0, c, or plus c, plus or minus c. Okay? And go back to our picture here, and you have 0 on x, 0 on y, plus c, minus c. So that is why you can't have anything between minus c and plus c. Because otherwise you can have a negative number equal to a positive number. Can't happen. But outside of that, then it looks just like before. Yuck. Wait. Yeah. Outside of that, where this is something positive, I mean, z is greater than c, or less than minus c, so that ratio is greater than, the ratio squared is greater than 1, okay? Then you have ellipses when you cross above or below. Okay. And when this is greater than 1, you have it's hard to say with that minus sign there, but you still have your hyperbolas like you normally would. Okay. Because set the y is equal to some constant, move them over here, and as long as z over c is greater than 1, z over c squared is greater than 1, then this is something you can pull back here, and you would have a minus this thing, and you have your hyperbolas again. Sort of hard to show analytically, with the numbers, but that's what you get. The top one is just obvious. Okay, so those are hyperboles. You have that a minus 1 on the right hand side. Even if you pull over the z over c squared, make it minus like I did above, then you have a minus 1 on the right, and that means the basically it means you have a plus term here, a plus term there, and you bring this over, it's a minus term. That means this one has to dominate these two. Yeah. Make that be. Okay. And that means that has to be greater than the minus 1. So that's what you get. Okay. And those are your drawings of them. We are out of time, aren't we? Sorry about that. I didn't know we ran over it. I lost my 5-minute break. Okay. Did I ever mark the roll? I don't think I did. Both of you are here, in case you hadn't noticed that. No, wait. We're missing Victor. He wasn't here. Okay. Treddy's here. Whoa, I put you in the wrong day. Treddy's here. No, I marked you here. I was marking off for my next class. Okay, I already got you here, and I already marked Warren Nelson. Okay. Sorry about that. I don't know where my brain is.
Can we still take a 5-minute break?
Wait, yeah, take a 5-minute break. Sorry about that. Treddy and McGrew, we haven't seen from the beginning, and Victor is absent. I was looking at the wrong class. Okay, I was looking at Jasmine. Okay, bye-bye. See you tomorrow. Yeah, let's take a break.